and welcome to Aviation Training Center. I'm Steve Ellisberg, President and founder of the company, and this is our new private pilot course. You're going to get a lot of information here, and if you follow through the course the way we ask, there's no reason you can't make a perfect score on the new FAA written exam. Jeff Doder and I together will teach you this course. If Jeff wasn't the best instructor out there, he wouldn't be here with me. Jeff, why don't you tell us about your qualifications and anything else you'd like to talk about before we start?
Thanks, Steve. Like Steve says, I'll get the job done like I have for the past 10 years. My professional background includes a BS in aeronautical engineering. I have 9,000 hours, and it's kind of funny how they add up. 15 years ago, I was a captain on a DC-9 working for Uncle Sam in Southeast Asia. Now I'm a co-pilot on a Boeing 737 for a major U.S. airline, working my way to captain. In a big successful airline, it can take 15 years. And in between these two jobs, I've worked for other airlines as a pilot and in training departments. So I feel pretty qualified to teach this course with Steve. We've divided the curriculum into 10 modules and use lots of animation and location footage to bring the topics to life.
These modules are aerodynamics, Airman's Information Manual, weather, federal aviation regulations, instruments, engine operations, weight and balance, performance, and navigation. Also, Ray Estes, an FAA flight examiner, will join us to talk about the flight check for your license. We've put them in this order on purpose and want you to go through the course from tape 1 to the end and don't jump around. After each module, we'll cover all the FAA questions you'll see on the real test. This will be fun because most answers should pop right off the page. Plus, we use computer graphics and multiple cameras to make learning them easy. Now, I'll explain how we lay out your course book. The first section is a detailed explanation of the subject we will cover, but we won't be following the book with the video. Next is the identical FAA questions we'll cover after each module. They're the exact questions you'll see on the FAA test. The next two sections are the appendix. Appendix 2 has lots of valuable reference material that will help you answer some test questions. And Appendix 3 has the actual charts that we use throughout the exam. We'll talk more about the test before we start our first group of questions. So let's get started with the course.
Aerodynamics is a study of the forces produced by the flow of air. Obviously, while the airplane's in flight, this flow of air, or aerodynamics, plays a major part in determining how an airplane flies and what causes it to react in a certain way. We as pilots need to understand aerodynamics. For instance, just to understand what causes the nose to turn to the left as we add power during the takeoff. In our discussion of aerodynamics, we'll start first with a discussion of the different parts of the aircraft. The fuselage is the body of the aircraft without the wings or the tail area. The empennage is the tail area made up of the vertical stabilizer and horizontal stabilizer. On the vertical stabilizer is located the rudder, which controls the aircraft's yaw, or the movement of the nose to the left and right. On the horizontal stabilizer is located the elevators. Some airplanes, the entire horizontal stabilizer moves. These control the aircraft's pitch, or the movement of the nose up and down. Outboard on each wing is an aileron. As one wing's aileron is up, the other wing's aileron is down. When an aileron is down, it causes that wing to produce more lift. The other wing's up aileron causes less lift or drag, more drag on that wing, causing the airplane to roll or bank. Inboard of the aileron are the flaps. When the flaps are extended, this allows the airplane to descend without increasing its airspeed. Some general aviation aircraft and most high-performance aircraft have spoilers located on the top of the wing. This particular airplane doesn't have the spoilers, but when the spoilers are extended or up, they allow the airplane to descend without increasing its airspeed. Next, we'll be discussing the four forces that act on an airplane. The first force that we'll discuss is lift. Bernoulli's principle states that in a fluid, as speed increases, air pressure or pressure decreases. And for aerodynamicists, airflow is considered a fluid. So as airspeed or the flow of air increases, pressure in that area will decrease. As we can see from this wingtip, a molecule of air traveling along the upper surface of the wing travels in a further or longer direction since it's curved than a molecule of air traveling along the bottom of the wing. This faster speed along the top creates lesser pressure on the top and more pressure on the bottom, and this is lift, which goes in basically an upward direction. Actually, lift acts perpendicular to the relative wind, and the relative wind is just opposite to the flight path of the airplane. As we're in a descent, this relative wind would be more from the bottom of the wing, and in a climb, the relative wind would be more from the top of the wing. Now we can consider all of the lift along a wing acting in one spot, called the center of pressure or the center of lift. In all conventional airplanes, this center of pressure is located behind or aft of the center of gravity. And we'll talk more about the center of gravity in just a few moments. As you control the location of that center of pressure by varying your pitch, you're controlling the aircraft's maneuverability and controllability. Next, we'll move to drag. Drag is the second force acting on the airplane. Drag is in two main forms, induced drag and parasite drag. Induced drag is produced anytime lift is produced. So anytime you're flying, you have induced drag. Induced drag decreases as airspeed increases. Parasite drag is made up of three basic types: form drag, friction drag, and interference drag. Form drag is produced when the wind flow is blocked. A streamlined shape would produce less form drag than a flat plate. So you see here the spinner or the streamlined cowl area produces less form drag than the flat areas behind the propeller. Skin friction is a second type of parasite drag. It's produced by rough surfaces interfering with the airflow. This view of the right wing gives a good contrast between the areas that are relatively smooth, the white painted areas that you see, and the dark area, which you can see is relatively rough. It would produce more skin friction drag. Interference drag, the third type of parasite drag, is caused when the airflow around two dissimilar air shapes interferes with each other. In this shot of the wing root, or where the wing impacts or touches the fuselage, the airflow around the wing will interfere with the airflow around the fuselage, producing interference drag. Parasite drag increases as airspeed increases. And the total drag, is shown by the U-shaped curve, has a low point which corresponds with lift over drag max, L over D max. We'll be talking about that in more detail later. Drag acts towards the rear of the aircraft. Thrust, which is the third force acting on the airplane, is produced by the propeller or jet engines. Thrust acts towards the front of the airplane. Weight, which is the fourth force acting on an airplane, would act in a downward direction, and it's sometimes called gravity. Now, in steady state unaccelerated flight, such as straight and level, or a steady state climb, or a steady state descent, the sum of the forces is zero. In other words, thrust would equal drag, and lift would equal weight. Now let me cover a couple of definitions. The first one is chord line. The chord line is simply the straight line from the leading edge of the wing drawn to the trailing edge of the wing. You might also hear the term chord, which is just the distance from the leading edge to the trailing edge. Another definition is camber. That's simply the measurement of the curvature of the wing. The more curved the wing is, the more camber it's said to have. I'll use a model to describe the next term, and that's wingspan, which is simply the horizontal distance from one wingtip to the other. The angle of incidence is defined as the angle that the wing is attached to the fuselage. And by angle, we're talking about the leading edge of the wing up or down associated with the fuselage. Obviously, the angle of incidence cannot be changed by the pilot. The angle of attack, however, can be changed by the pilot. It's defined as the angle between the chord line and the relative wind. Now, the pilot can change the angle of attack by changing his pitch. Increasing the angle of attack usually results in moving the center of pressure forward and in increased lift. If you increase the angle of attack too much, though, you'll enter into a stall. Now, a specific wing will stall at only one angle of attack. This is called a critical angle of attack. Stalling is not directly dependent upon airspeed. If you change the gross weight, the angle of bank, or the load factor, this will result in an increased stalling airspeed. Now, if you enter a stall uncoordinated, this could result in a spin, which is simply the downward moving flat spiral. If you're in a spin, the inside wing is stalled, while the outside wing is still producing lift. Next, we'll look at the axes of the airplane. The longitudinal axis goes from the nose to the tail. The aircraft banks or rolls about the longitudinal axis, and movement about the longitudinal axis is controlled by the ailerons. The vertical axis goes from the top of the aircraft to the bottom. The aircraft yaws about the vertical axis, and movement is controlled by the rudder. The lateral axis goes from the middle of one wingtip to the middle of the other wingtip. The aircraft pitches, nose up or nose down, about the lateral axis, and movement is controlled about the lateral axis by the elevators. All three axes intersect at the center of gravity. And the center of gravity, abbreviated CG, is a point on which the airplane would balance. Remember, on conventional airplanes, the center of gravity is ahead of the center of pressure. This causes the aircraft's nose to pitch down during a stall. If we would move the center of gravity back towards the center of pressure by moving weight in the airplane, this causes the airplane to become less stable, but it decreases the stalling speed and it makes the aircraft more fuel efficient. If we move the center of gravity forward, again by adjusting weight, this makes the airplane more stable and increases the stalling speed. Extending the flaps changes the camber and the chord line of the airfoil. When the flaps are lowered, this provides more lift and drag, and the stall speed is lower. You can descend more steeply without increasing airspeed when you use flaps. The main types of flaps are plain, split, slotted, and Fowler. The aspect ratio is the ratio between the wing span and the wing chord, or in other words, the wing span in feet divided by the chord in feet. The higher the aspect ratio, the more lift is generated. General aviation airplanes have a high aspect ratio wing, and the advantages of this are they're more forgiving and they can operate at lower speeds. Low aspect ratio wings have advantages and disadvantages over high aspect ratio wings. Some advantages are they have greater structural strength and they're more aerodynamic or more streamlined. A disadvantage is that it's sloppy at slow speeds. Wing dihedral is the upward angle of the wings as they're attached to the fuselage. This dihedral tends to right the airplane if a side slip occurs because the down wing would have a greater angle of attack and produce more lift. The wing shape has something to do with stall characteristics. A rectangular wing tends to stall first at the root, giving you some warning of an impending stall. Swept-back wings, on the other hand, stall first at the wing tip, which is closest to the aileron and therefore more dangerous. Aerodynamicists use the term stability when referring to aircraft, and all stability refers to is the airplane's tendency to return to its original position after being disturbed. For instance, with this model, let's say we move the right rudder, causing the nose to move to its right. If an airplane was said to be positively stable, the nose would return to its original position. If, however, after moving the nose to the right by hitting the right rudder, the aircraft were negatively stable, the nose would continue to move farther away from its original position. Or, after moving the nose to the right with the right rudder, if an aircraft was said to be negative or neutrally stable, the nose would remain in that position. It wouldn't move farther away from the original position and wouldn't move or return to its original position. Now, there are two main types of stability: static stability and dynamic stability. Static stability is the stability I just referred to. In other words, the tendency to return to its original position. Dynamic stability has to do with the oscillations of the airplane. In other words, when let's say the airplane were positively statically stable, it returns to its original position. It would not, however, just stop right in its original position. It would overshoot its original position slightly and then come back towards its original position, and the oscillations then are what we're talking about when we say dynamic stability. If the oscillations get smaller and smaller about its original position, then it's said to be positively dynamically stable. If, however, the oscillations get bigger and bigger about its original position, now the airplane is said to be negatively dynamically stable. You'll also hear the terms longitudinal, lateral, and vertical stability. And don't get uptight. These are just the terms of what happens to those particular axes. Let's take longitudinal stability. That has to do with what happens to the longitudinal axis, which is, remember, from the nose to the tail, and that's about the lateral axis. So longitudinal stability would be stability in pitch. Or lateral stability is what happens to the lateral axis, which is wingtip to wingtip, about the longitudinal axis. In other words, roll. And then vertical stability is what happens to the vertical axis, and that is yaw. Now let's talk about the term load factor. The load factor is just the weight that this particular airplane would need to support in flight while flying. Now, right here on the ground, obviously, the load factor is 1. We're just pulling 1 G. In flight, in straight and level flight, the load factor would also be 1. So the weight that the airplane's wing would have to support while in flight would just be 1 times the gross weight of the airplane. If the particular airplane were experiencing a load factor of 2 while in flight, then this particular wing would have to support 2 times the gross weight of the airplane to keep it level. In this load factor versus indicated airspeed chart, the normal operating range is enclosed by the dotted lines. If you're above the line from B to D, or in other words, pulling more Gs, or to the right of the line from D down, then you're in the structural damage area, where you could, in fact, damage the airplane. While you're straight and level, the lift vector, remember, points basically straight up. In a turn, the lift vector moves to the side. While you're in the turn, the vertical component of lift keeps the aircraft up, and the horizontal component of lift turns the aircraft. As airspeed increases, bank angle must increase to maintain a certain rate of turn, or in other words, a certain number of degrees per second. Or in a constant bank angle, if your airspeed increases, the radius of turn will also increase. Adverse yaw is caused when you roll into a turn. As you roll into the turn, the aileron on the up side, or the up wing, is producing more lift, so that side also has more drag because of induced drag. This causes the aircraft to yaw opposite to the direction of turn. You would fight this or combat this by using more rudder in the direction of turn while rolling in and rolling out. There are several left turning tendencies which are greatest when the aircraft is slow and at high power settings. The first of these is due to torque. One of Newton's laws states, for every action there is an equal and opposite reaction. The propeller, as seen from the cockpit or from the rear, turns clockwise. This causes the aircraft to turn in the opposite direction, or counterclockwise, and to bank left and move the nose to the left. You would fight this by using greater rudder pressures in right turns than in left turns. In some aircraft, the left wing is mounted at a higher angle of incidence than the right wing, and this is called rigging. And this is used to counteract torque at normal cruising airspeeds. At slower speeds, however, this difference in lift causes the airplane to yaw to the left. The third left turning tendency is slipstream or corkscrew effect. The air from the propeller moving around the plane, and it strikes the vertical tail on the left side, moving the nose to the left. And the last left turning tendency is caused by P factor. Remember P for propeller. At the slow airspeeds, your angle of attack for the entire aircraft is greater, or nose up. The descending blade on the right, therefore, takes a larger bite of air than the rising blade on the left. This causes the nose to be pulled to the left. Lift versus drag, remember, is a measure of aerodynamic efficiency. In this chart, we see L over D plotted against angle of attack. The highest point of the curve corresponds with L over D max, or lift over drag max. And L over D max is also the lowest point of the total drag curve. So when L over D is at its maximum, this would be the most efficient angle of attack, such as for a power-off glide. Ground effect occurs within one wingspan of the ground, and within that one wingspan, the aircraft is actually more efficient. This is caused by the ground changing the direction of the relative wind and decreasing the force of the wingtip vortices. Within ground effect, the required angle of attack for flight is less, there's less induced drag, and there's more lift. And the last item we'll want to cover in aerodynamics are the control positions that you would want to maintain while on the ground while taxiing with a crosswind. This is mostly for high wing airplanes. Let's say we had a headwind, either a right quartering headwind or a left quartering headwind. Let's say right quartering headwind. You want to maintain the elevators neutral, neither up nor down. You want to maintain the upwind wing's aileron up. This would cause that wing to be forced down and keep it from being picked up by a wind gust and turning the airplane over. In a tailwind situation, let's say we have a left quartering tailwind. You want to maintain the elevators, in this case, with a tailwind situation, down, keeping that tail forced down, and you want to maintain the aileron on the upwind side also down, keeping that wing down and not being picked up by a wind gust. And that's it for aerodynamics. As I said before, we as pilots need to understand aerodynamics to understand what's happening to our aircraft while we're in flight. And the more you understand, the more in control you'll be. Steve, since you're the former FAA written examiner here, why don't you cover the mechanics of taking the FAA test before I start with the questions?
Okay. First, you'll be taking a multiple choice test. You'll be asked 50 out of 800 or so possible questions. The FAA examiners give the test, not the FAA. And since there's over 1,000 examiners, it'll be easy to find somewhere to sit the exam. Your instructor, FBO, club, or local FAA office can tell you where to go. Back in the late 70s, the FAA turned this testing over to the industry, and at the same time, they published the unabridged test booklets. This book is available to anyone, but the FAA does not publish the answers. There's absolutely no difference between the examiner's question book and the one we've included in your course. Here's how the test works. Always put an answer down, even if it's a wild guess, because there's no penalty for wrong answers. It's a pass-fail exam. 70% is a passing score, so if there's 50 questions, you can miss up to 15 and still pass. You want to answer each question based on the latest regulation or procedure, and we have a saying here that we've said for the last 12 years, RTFQ. You know what that means? Read the funny questions. Always make sure you understand the problem the question asks before you even look at the answers. We can't emphasize this enough, but will as you work hundreds of questions with us. Watch out for absolutes and determiners, words like always or entirely and most likely or usually, because they're almost always wrong. We don't go over wrong answers, so let's get started. Let's see what you learned. Let's look at some identical verbatim FAA questions. When I say identical and verbatim, I mean these are word for word identically what you're going to see on the FAA test.
When we cover these questions, we'll be talking only about the correct answer for the most part. Once in a while, we'll give you some examples of why certain answers are wrong, but most of our examples or questions we'll be talking about the question and then the correct answer, and that's all we're going to talk about. And this you can use to reinforce the correct answer so that when you actually take the test, these correct answers will just leap up out of the page right at you. Also, all of the questions have 4 numbers. They all start with 1 for the private pilot. So it's 1,000 and whatever. We'll be dropping the first 1,000. So when we mention question number 205, that's really 1,205. It just saves us a little bit of time not covering the thousands number.
Let's get started with the aerodynamic questions. We'll be on page 7. Our first question is number 84. You with me? Okay. The 4 aerodynamic forces acting on an airplane are?
Number 4, thrust, lift, weight, and drag.
Question number 85. When are the 4 aerodynamic forces that act on an airplane in equilibrium?
It's answer number 4, during unaccelerated flight.
Question 86. What is the relationship of lift, drag, thrust, and weight when the airplane is in straight and level flight?
It's answer 4, lift equals weight, and thrust equals drag.
Question 87. What makes an airplane turn?
That's the horizontal component of the lift. Remember when we actually bank, our lift vector changes from going straight up to off to the side a little bit. That horizontal component is what actually makes the airplane turn. That's answer 3.
Question number 88. One of the main functions of flaps during the approach and landing is to?
It's answer 3. To increase the angle of descent without increasing airspeed.
And when do you use flaps most of the time?
Mostly just in the approach phase or for takeoff. So you use the flaps to decrease the landing roll on takeoff, and then on landing, decrease the takeoff roll on takeoff, and then on landing to slow down and to get down without increasing speed on takeoff or on the landing phase.
Great. Now we have a chart we're going to go to, which is figure 7 back in your appendix. Question 89, refer to figure 7. The acute angle A is the angle of?
Let's look at figure number 7 in the back. And when they say acute angle, they're just talking about less than 90 degrees. So the acute angle, or less than 90 degrees of A, shown in this diagram, is between the relative wind and the chord line. And that's the definition of the angle of attack. That's answer number 2.
Question number 90. The term angle of attack is defined as the?
Answer 1, the angle between the wing chord line and the direction of the relative wind.
Next question is 91 on page 8. Refer to figure 8. That will be back in your appendix. If an airplane weighs 2,300 pounds, what approximate weight would the airplane structure be required to support during a 60-degree bank turn while maintaining altitude? Kind of a long question.
We're just talking here about how what your load factor is going to be during a 60-degree bank turn. And so that's all we have to do is we look at our figure 8, and we'll see that during a 60-degree bank turn, the load factor, if we read up to the curve and then over to the side, the load factor, as they say here, is 2. So for a 60-degree bank turn with a load factor of 2, we just multiply that 2 times the aircraft weight, which was given as 2,300 pounds. That's 4,600 pounds. Answer number 2.
I'd like to mention, next time you're in a plane making a turn, you might want to get in a 60-degree bank turn, 55 or 60 degrees, maintain level flight. To do that, you're going to need a lot of back pressure. You know that. Try to lift your feet up off the floor, and you'll see that your feet weigh twice as much as, they're going to feel about twice as heavy as they normally are, indicating that there are 2 G's pulling against you. But this will only happen if you maintain level flight. Question number 92. Refer to figure 8. If an airplane weighs 3,300 pounds, what approximate weight would the airplane structure be required to support during a 30-degree bank turn while maintaining altitude?
Okay, again, we'll go to figure number 8, looking for 30 degrees, starting on the bottom here. 30 degrees up to the curve is just above the 1 line. This line is 1G. Just above 1G. Looks like about 1.2 maybe. So we'd multiply that 1.2 times 3,300 pounds, which is given in the problem, and that comes out with 3,960 pounds. That's answer number 2.
Question number 93. Refer to figure 8. If an airplane weighs 5,400 pounds, what approximate weight would the airplane structure be required to support during a 55-degree bank turn while maintaining altitude?
Well, the steps in this case are exactly the same. We'll go to figure 8 and look at 55 degrees. 55 degrees up to the curve is more than 1, not quite 2, and it's more than 1.5. Looks like it's about 1.7, reading across to the side, 1.7. So take that 1.7 and multiply it by the given weight again, 5,400 pounds, and that's equal to 9,180 pounds, which is answer number 3.
Question number 94. This will be the last time we're using this chart. Refer to figure 8, the maximum bank that could be made during a level turn without exceeding the maximum positive load factor of a utility category airplane, which is 4.4 G units, is?
Well, in this case, we start off on the side of the chart. We enter in at the number of G's given, it's 4.4, and go over to the curve and then read down to find the angle that would give us the angle of bank. So we start at 4.4, which is given in the problem, and read over 4.4 to the curve, and then down. Looks like it's more than 70, not quite 80, right about here, about 77 degrees. That's answer number 3, 77 degrees.
I guess the point here that can be inferred out of these questions is, first of all, I hope you realize you can never make a pure 90-degree bank turn in an airplane and maintain altitude. It's impossible. And even if you're ever even thinking like an 80-degree turn at 77 degrees, if you're maintaining altitude, you're just about pulling the wings off that plane. You'll feel it. You wouldn't be able to move your feet off the floor in a 77-degree bank turn maintaining altitude. Question number 95. The left turning tendency of an airplane caused by P factor is the result of the?
P factor is propeller, so it's answer 2. Propeller blade descending on the right, producing more thrust than the ascending blade on the left.
Well, that's pretty easy, Jeff. As long as we remember that P is propeller, we know the right answer. It's the answer that starts with propeller.
Right.
Okay, question 96. The purpose of the rudder on an airplane is to?
It's answer 1. It controls the yaw, or where the nose goes, left or right.
Question number 97. A purpose of wing flaps is to?
Well, we spoke about this a little bit before. It's answer 1, to enable the pilot to make steeper approaches to a landing without increasing airspeed.
Which is something we might want to do when we have obstacles at the end of the runway.
Certainly. Sure,
Okay.
we could come in over those and not be faster than normal.
Question number 98. The amount of excess load that can be imposed on the wing of an airplane depends upon the?
The amount of excess load just depends upon the speed of the aircraft. That's answer number 2, speed of the airplane.
Question 99. During an approach to a stall, an increased load factor will cause the airplane to?
It's answer 1. It caused the airplane to stall at a higher airspeed.
Question 100. Which basic flight maneuver increases the load factor of an airplane on an airplane as compared to straight and level flight?
Well, remember we just talked about that figure number 8. As you increase the bank, the load factor increases. So it's turns. It's answer number 2.
Question 101. An airplane said to be inherently stable will?
Well, if it's stable or inherently just means that normally or naturally it's a stable type of airplane. It is easier to control and requires less effort. So it's answer 3, requires less effort to control.
Question 102. What determines the longitudinal stability of an airplane?
Remember, longitudinal stability is stability about the lateral axis. In other words, that axis between the wingtips. Longitudinal stability is what's happening to the longitudinal axis. So we're talking pitch in this case, nose up, nose down. And we talked about how when you move the CG closer to the center of pressure or the center of lift, how you become less stable. That's answer 1, the location of the CG with respect to the center of lift.
Question number 103. What causes an airplane, except a T-tail, to pitch nose down when power is reduced and controls are not adjusted?
Well, the answer is number 2. The downwash on the elevators from the propeller slipstream is reduced and elevator effectiveness is reduced.
Question 104. An airplane has been loaded in such a manner that the CG is located aft of the CG limit. One undesirable flight characteristic a pilot might experience with this airplane would be...
Well, if the CG is aft of the aft limit, we're out of limits. And remember, as you move that CG or center of gravity aft, the airplane becomes more squirrely or more difficult to control precisely. So if you would get into a stall, for instance, you might not be able to recover. That might be one problem from an aft CG. Or another problem might be that you couldn't even control the airplane. You actually couldn't even fly. So it's answer number 2, the inability to recover from a stalled condition.
Yeah, one reason is you run out of elevator pressure trying to compensate for that rearward CG. And like you say, if you were to inadvertently then go into a spin, good chance you wouldn't even be able to recover. You wouldn't have the control effectiveness. Question number 105. Loading an airplane to the most aft CG will cause the airplane to be...
If it's most aft, then it's answer 4, less stable at all speeds.
Okay, we'll skip a question down to 107. P factor causes the airplane to...
Remember, P factor again is caused by that propeller descending blade on the right taking a bigger bite out of the air than the ascending blade on the left, causing the nose to yaw to the left. It's answer 2, yaw to the left when at high angles of attack.
Next question is number 110. In what airspeed and power condition is torque effect the greatest in a single-engine airplane?
It's answer 1, low airspeed and high power settings.
Question 111. The angle of attack at which an airplane wing stalls will...
It's called the critical angle of attack, and that angle of attack, the critical angle of attack, is the same for the wing no matter what. We're not talking airspeed, so we're talking strictly critical angle of attack. So it's answer 3, it will remain the same regardless of gross weight.
Question 112. As altitude increases, the indicated airspeed at which a given airplane stalls in a particular configuration will...
Answer 3, it will remain the same as at low altitude.
Question 113. During a spin to the left...
It's answer 3, the left wing is stalled and the right wing is not stalled. Now, remember, to enter a spin, you have to be in a fully stalled condition. And also, while you're in the spin, after you've started the spin, one wing is stalled and one wing has not stalled. So the wing that is on the outside of the turn is the one that is not stalled, and the wing that is on the inside of the turn is stalled. So it's answer 3.
Now, I'd like to point something out to you young aviators, that the way you're going to practice stalls is to slow the air, to look for clearing turns, look for traffic, make sure you're probably 2,500 feet above ground level, pull the power back, carb heat on, pull the elevator back until you get the stall. That's the way you're going to practice. You'll also see accelerated stalls in a turn. But I want to make the point that you can stall that airplane in any flight configuration with abrupt control movement. And anything abrupt, including a lot of turbulence or shear, can cause that airplane to stall and can create a spin. So don't think that the only way to get an airplane in a spin is the classic way you're going to learn in your flight training. Another thing I'd like to advise is that in your flight training you ask your instructor to demonstrate some spins, so you don't go all the way through this thing, or I'm referring to your training, with not knowing what a spin is or being afraid of it and having heard the term a lot. It's something that a lot of people are scared of because they don't understand it. There's really nothing to it. It's really quite exciting. Make sure you ask your teacher to do it. A lot of the teachers now don't do it because the FAA no longer requires spins for certification. Back in the 70s, there were quite a few airplanes auguring into the ground due to poor spin characteristics, namely Grumman Tigers were real bad in the Grumman series. So with these accidents, the FAA stopped them. But it's something you should know. If for some reason your instructor can't do it, find an aerobatic instructor with an aerobatic airplane. They'd be happy to take you up and show you how this works. Question number 114. In what flight condition must an aircraft be placed in order to spin?
It's answer number 3, stalled.
Okay. 115. Ground effect is most likely to result in which problem?
Remember, ground effect is what occurs when you're within about a wingspan of the ground and the airplane is much more efficient, or at least the wings are, and you have more lift and less induced drag. But the problem with that is you might be very heavy, lift off into ground effect, and then once you climb out of ground effect, suddenly you cannot fly. You're not fast enough to actually produce enough lift for the wings. So it's answer number 2, becoming airborne before reaching recommended takeoff speed.
Next page, question 116. Which phenomenon must a pilot be aware of as a result of ground effect?
It's answer 4, the induced angle of attack and induced drag decrease.
That's a fun answer. Question 117. After takeoff and after leaving ground effect, the pilot will need to...
After you leave ground effect, remember the airplane now is becoming, the wing is less efficient, so you're going to have to pull back on the nose just a little bit, keep that nose up, or pull it up a little bit. It's answer 3, increase pitch attitude due to a nose down change in moment.
Question 118. Floating caused by the phenomenon of ground effect will be most realized during an approach to land when...
Well, the answers, if you look through the answers, what they're looking for is when do you get into ground effect? And remember, the answer is that within one wingspan of the ground. There's no answer there that is exactly that. Answer 1 is most correct. It's at less than the length of a wingspan above the surface.
Question 119 will refer to a figure back in your appendix, figure 9. We're going to make it easy for you. Anytime an illustration or figure comes up, we're just going to show it to you right here on television. So you can either go back in your book or follow us on the TV. Question 119. How should the controls be held while taxiing a tricycle gear-equipped airplane into a left quartering headwind as depicted by A in figure 9?
Well, let's look at figure 9, and it talks or it shows us arrow A here, just giving us an idea of what a left quartering headwind would look like if you're having trouble visualizing that. Remember, when you have a left quartering headwind, we're talking about tricycle landing gear aircraft. You want to get the upwind elevator, or excuse me, the upwind aileron up. That will keep that left wing from being picked up by a gust of wind. And you want to neutralize the elevators. Don't have them up or down. So the left aileron would be up, the left aileron will be up, and the elevators will be neutral. So it's answer 1, left aileron up, neutral elevator.
Question number 120. How should the controls be held while taxiing a tricycle gear-equipped airplane with a left quartering tailwind as depicted by C in figure 9?
Okay, again, we're talking about a tricycle landing gear aircraft. Arrow C is showing a left quartering tailwind. Again, we want to keep that upwind aileron down so that we won't pick up the wing and by a gust of wind. And we want to keep our elevators down so that the tail won't be picked up. So it's answer number 4, left aileron down and down elevator.
Question number 121. While taxiing a tail wheel equipped airplane into a right quartering headwind, as depicted by B in figure 9, the right aileron should be...
Okay, now we're talking about a tail wheel equipped aircraft, in other words, a tail dragger, and we have arrow B. The wind is coming from the right and in front of us. In a tail wheel, we want to keep the elevators up, and that would keep the tail pushed down towards the surface of the ground, and we want to keep that right, the upwind aileron up also. So it'd be answer number 1, the right aileron should be up, and the elevator should be up.
Question number 122. While taxiing a tail wheel equipped airplane with a right quartering headwind, as depicted by D in figure 9, the right aileron should be held...
Well, the tailwind in arrow D is showing us that it's right quartering tailwind. And again, this is a tail dragger, so we're talking about a tail wheel equipped aircraft. The right aileron would be down, keeping that wing from being picked up. And the elevator would be down, keeping the tail from being picked up by a wind gust. So it's answer number 4, right aileron down and elevator down. All these talking about are really book answers or school answers. In the real world, you might have winds coming from, let's say, the left quartering headwind to a headwind to a right quartering headwind. So you might have to, if it's strong enough wind, might be having to change the controls all throughout the taxi.
Another interesting point is, let's say your stall speed on your aircraft is 57 miles per hour. It could be knots, whatever. Let's just say you're sitting on the ground and a 60 knot gust comes by. What do you think is going to happen? You're right, the plane's going to fly. Well, how long do you think it's going to fly for? It's going to fly long enough to lift up a couple feet and probably blow over. Crosswinds are fascinating. As a bush pilot in Alaska, I used to find myself occasionally landing, instead of horizontally on a runway, vertically on 150 feet, like in Cold Bay, Alaska, in a small Cessna, using that 150 feet instead of 6,000 because of such strong winds. When you get into strong winds on the ground, you're going to have to do whatever it takes to make it work right. And everything you're seeing here with the FAA isn't exactly how it'll take place in real life. This pose any problem to you in a big jet on the ground?
No.
Don't pay attention to them.
You don't even behind an airplane that happens to be running up its engines, you don't worry about it at all. It's just, you know, when you're talking about 130,000 pounds for an airplane, which is relatively small in airliner circles, there's really no problem in taxiing.
Good. Question number 123. When taxiing with strong quartering tailwinds, which aileron positions should be used?
Okay, tailwinds, you want to have that aileron down. So the answer 4, aileron down on the side from which the wind is blowing.
Question 124. Which aileron positions should a pilot generally use when taxiing in strong quartering headwinds?
It's answer number 1, the aileron up on the side from which the wind is blowing.
Okay, next question is 125, and it's the last of our aerodynamic questions. Which wind condition would be most critical when taxiing a nose-wheel-equipped high-wing airplane?
Well, it's answer number 4, a quartering tailwind, because that can pick up either the wing or the tail, and so that's why we answer quartering tailwind.
Let me bring up another real-world example. Let's say you're in a situation where you have a 30 or 40 knot quartering tailwind in a light Cessna and you're just about getting blown over. The first thing I would do is roll the thing at least around into the wind, keep the engine running to give me a little control on the ground. Let's say you're barely able to hold it. Let's say you're like this, and boy, what's going to happen? You're afraid to move. The wheels are literally jumping off the pavement. I'd get on ground control and tell them to get a couple of personnel out there to come and hold down the wings. This is more of a problem on high-wing airplanes than low-wing planes. It might be interesting to note also that in areas of the world where there are high winds all the time, like in Alaska and in a lot of the bush areas, low-wing airplanes are much more popular than high-wing airplanes in strong wind conditions. So that'll wrap it up for aerodynamics. As you see, we covered a lot more in the theory section than you need to know with the questions. And that's our goal here, is to teach you as much as we can in this course, not to just teach you the bare minimums for the FAA test.
The Airman's Information Manual is our reference source on airport operations, airspace regulations, and general piloting techniques and procedures. It's often referred to as the Airman's Bible and contains everything you need to know about VFR and IFR flight. Steve's only going to cover the areas which you'll be tested on, since a full review of the EIM would take longer than this entire course. In this module, you'll learn about flight plans, airport operations, runway markings, wind indicators, approach lighting systems, and some of the physiological considerations we pilots must learn to deal with.
There are a few pre-flight items that you should always do, and that's a walk-around inspection of the aircraft. And if a plane has been stored for a while, check for damage or intrusions caused by animals, birds, or insects. Plus, the use of a written checklist for pre-flight inspection and starting the engine is recommended. This helps to ensure that all necessary items are checked in a logical sequence. Automatic Terminal Information Service, or ATIS, is simply a recording that the tower puts out every hour and gives the basic information about landing, takeoff, weather, and communications for that airport. And if the weather or winds change significantly, they'll put out a special recording before the normal hourly change. Let's listen to an ATIS.
Controller on initial contact, you have X-ray. Jeffco Airport Information X-ray, 1645 Zulu weather. Sky conditions better than 5005. Temperature 61, dew point 32. Wind 1507. Altimeter 2984. Visual approach and use, landing into prime runway 11 left. Notice airmen, Jeffco glide slope out of service. Use caution for men and equipment working on and near runway 220. Advise controller on initial contact, you have X-ray.
ATIS frequencies are shown on aeronautical charts for airports that have it. and you listen before contacting ground control, or when inbound to land before you call the tower. So to sum it up, ATIS is the continuous broadcast of recorded information concerning non-control information in selected high-activity terminal areas. On initial contact, you tell the controller you have the ATIS information by giving him the alphabetical code word such as Sierra, Tango, or Uniform. The phrase "have numbers" means you have the wind, runway, and altimeter setting for the airport. The term initial contact means the first radio call you make to an FAA facility. Generally, the prefix N before the airplane's call sign is omitted, and the make and model of the airplane is sometimes stated. For example, Cessna 12345 or Cessna 172 12345. Ground stations have call signs too, or you might say names. For example, Miami Flight Service Station is called Miami Radio. An FSS, or a flight service station, that has en route flight advisory service, or EFAS, is called Flight Watch, like Chicago Flight Watch. And the frequency will always be 122.0. Airport traffic control towers are called towers. For example, LaGuardia Tower. Radar controllers that lead you in and out of busy areas are called approach control and departure control for the area they serve, like Memphis Approach or Los Angeles Departure Control. An en route radar center is called center, like New York Center. Last, airports without towers use Unicom, which is a frequency provided for pilots to give their intentions to each other. Sometimes an operator on the ground will give you known traffic, winds, and an altimeter setting. Airports served by Unicom use the word Unicom after the airport name when you're talking to the operator on the ground. Numbers for altitude and winds are given like this. 500 is called 500. 900 is 900. 4,500. 10,000. 13,500. For speed, it's 9 or 5 knots, or 180 knots, and so on. In directions, 005 would be 5 degrees. 220 would be 220 degrees. Radar advisories are given to pilots to help spot other traffic. Controllers give them according to the clock method in relation to your ground track. These advisories don't take into account the fact that you crab into the wind to maintain a specific track over the ground. Okay, we have a clock here to help show you how radar advisories are given. It doesn't matter that it's 1:30, and it doesn't really matter what direction it is. We'll always reference 12 o'clock to the nose of the aircraft. So if you're heading, let's say 360, and ATC says traffic at 10 o'clock, 2 miles southbound, where would you look for the traffic? Well, let's first think, where's 10 o'clock in relation to the nose of our plane? It's off to the left, and to the left of north is northwest. Let's take one more example. Let's say ATC says traffic 2 o'clock, 5 miles southbound, and they want to know where you would look for traffic. Okay, 2 o'clock's over here. It would be somewhere right of your nose, somewhere between your nose and 90 degrees. Pretty easy to understand, and it's really easy to understand once you get in the air and get radar advisories. Next, we'll talk about VHF and DF steers. Before radar was so widely used, there was an extensive direction finding system in place at selected flight service stations and at radar facilities. All you needed to use this was a transmitter and a receiver. Then every time you clicked your mic, ground personnel could get a bearing on you and give you assistance or direction on where to go. Transponders communicate with radar facilities. Interrogation signals transmitted from the ground are received by the transponder. Then the transponder sends back a coded signal with 3 different types of information. First, the radar controllers can tell what code is selected, such as 1200, and 1200 is used for all VFR flights. Controllers can give you other codes when you're in radar contact. Never switch through 7700, which is for emergencies, unless you have an emergency. Never switch through 7600, which is for instrument pilots if they lose their communications. Technically, it's for any pilot who loses communications. And never switch through 7500, which is the hijacking alert. And the last code you never want to use is 0000, because that's reserved exclusively for the military. Second, push the ident feature only when told to do so. This makes your radar code intensify on the controller's screen. The ident light lights up when radar is interrogating your transponder. When you put it in ALT position, or the ALT position, this activates the altitude reporting feature called Mode C, and the controller using radar can read your airplane's altitude. And last, if ATC or air traffic control advises that radar service is terminated, the transponder should be set to 1200 from whatever previous code they gave you. Now, let's talk about wake turbulence. Wingtip vortices, also called wake turbulence, are twin horizontal tornadoes produced by any aircraft when it's developing lift. The higher air pressure on the bottom of the wing flows around the wingtip to the area of lower pressure on top of the wing. These tornadoes are at maximum strength when an aircraft is heavy, clean, and slow, or at maximum gross weight with landing gear and flaps up and at a slow airspeed. They sink below the aircraft, generating the turbulence, and move outward. When departing behind a heavy aircraft, pilots should avoid wake turbulence by staying above and upwind from the heavy aircraft. When landing, stay above the large aircraft's final approach path and land beyond its touchdown point. The wind condition that requires maximum caution on landing is a light, quartering tailwind because the vortices get pushed onto the runway. I want to tell you, wake turbulence is serious business. Even if you're behind a small commuter plane weighing 6,000 or 8,000 pounds on landing, you get in his wake turbulence, he can turn you right on your back, and full controlled deflection will not even bring you around. That's a real problem when you're close to the ground if you're upside down. Next, let's talk about runways. First, runways are painted with different markings. This is what a basic runway looks like. These arrows indicate a displaced threshold. Taxi and takeoff is permitted in this area, but no touchdowns are allowed until you pass the displaced threshold. Chevrons indicate an overrun, and this area should only be used for this purpose. And a closed runway is shown by X's. Never attempt an approach to a closed runway because there could be a chain across the runway. Airports have rotating beacons, so you can find them at night. Civilian airports have one white flash, then one green flash. Military fields have two quick white flashes between the green flashes. And if you see the rotating beacon on during the day, the field is below basic VFR weather minimums. A special VFR clearance or IFR flight plan will be required. And we'll talk more about this later. Now let's talk about traffic patterns. Standard traffic patterns use left-hand turns. Non-standard traffic patterns are right-hand turns. At tower-controlled airports, you take your instructions from the controllers. At non-controlled fields, comply with any FAA traffic pattern established for that airport. Pilots always want to take off and land into the wind, and there are 5 legs that make up a traffic pattern. They are upwind, crosswind, downwind, base, and final. Segmented circles are seen on the ground when you're flying over certain airports. The little L's indicate the traffic pattern or direction of turns you make to get lined up with the active runway. The wind cone in this illustration shows a wind from the northwest. So if you want to land into the wind or as directly as possible, you'd select runways 36 or 27. And runways are always aligned with magnetic headings you'll see on the aircraft's compass. And all they do is drop the last number when they number the runways. Runways 18 and 09 wouldn't be used because you'd be landing downwind, which would give you a very long and undesirable landing roll. The turns you'd make would be left for runway 36, left for 09, right for 1-8, and right for 2-7. This arrangement would prevent aircraft from approaching from the southeast. Next, we'll talk about the visual approach slope indicator. There are 4 types of light boxes installed at the approach end of some runways. They tell you if you're above, on, or below the recommended glide path to the runway, and are very helpful at night. The most common is 2-bar VASI. VASI stands for the Visual Approach Slope Indicator, which is exactly what it does. An above glide path indication will show white over white. An on glide path indication is red over white. Remember, red over white, you're all right. A below glide path indication is red over red. And our memory aid here is red over red, you're dead. So when approaching to land, you should maintain an altitude at or above the glide slope. Big airports have 3-bar VASIs. The 3rd bar, or you could say the most downwind bar, is used for jumbo jets because the pilot is so high off the ground. Small plane pilots don't use the most downwind bar. So here we see an on glide slope indication for a 3-bar VASI. A tricolor VASI is a single box near the approach end of the runway. Above glide path is amber color. On glide path is a green color. And below you would see red. PAPI is a precision approach path indicator, and it is similar to VASI except the lights are installed in a single row. High is all white lights. Slightly high, you'd see 3 whites and 1 red light. A non-glide path indication is 2 white and 2 red lights. Slightly below, you'd see 1 white and 3 red lights. And I'm sure you can guess what a below indication would be. That's right, 4 red lights. And the last system is called a pulsating approach slope indicator. Above glide path is pulsating white. On glide path is a steady white or alternating red and white light. And a below glide path indication is pulsating red. So much for approach lighting systems. Now let's look at runway lighting. Runways have edge lights that are white. The ends are marked with green if you're on approach. Taxiway lights are blue omnidirectional and show you the usable limits of taxiways. Some runways have high-intensity runway lights, and some of these can be controlled by clicking your radio's microphone on a specified frequency. Key the mic 7 times, and high-intensity lights come on. 5 times gives you medium, and 3 clicks gives you the lowest intensity lighting. The last area we'll talk about in the Airman's Information Manual is flight physiology. Hypoxia or oxygen deprivation occurs when the body isn't getting enough oxygen. Typical symptoms are drowsiness, dizziness, and a sense of well-being. The FAA says it's best to avoid flying above 10,000 feet MSL for prolonged periods without breathing oxygen. If your fingernails or lips turn purplish in color, this is a physical sign of hypoxia. Hyperventilation means excessive breathing. It's caused by blowing off carbon dioxide, and this can be caused by emotional tension, anxiety, or fear. Pilots can overcome this by slowing their breathing rate. Talking aloud or breathing into a bag can help. So says the FAA. Carbon monoxide is an odorless, colorless gas that is a byproduct of combustion. The most common source in flight can come from the airplane cabin heating system. Large accumulations of carbon monoxide in the human body can result in an increased sense of well-being, like hypoxia. Susceptibility to carbon monoxide poisoning increases as altitude increases. And if you ever expect carbon monoxide poisoning, shut off the heater, open the air vents, and land immediately. Spatial disorientation, also called vertigo, occurs when the body senses are telling you one thing, but your airplane is actually doing another. A state of temporary confusion resulting from misleading information being sent to the brain by various sensory organs is really what spatial disorientation is all about. Loss of the visual horizon can bring this on very quickly. The danger of spatial disorientation during flight in poor visual conditions may be reduced by having faith in the instruments rather than taking a chance on the sensory organs. So you always trust the instruments and not the different signals your body sends to your brain if you want to live long and to be an old pilot. There are some techniques you should know about for effective visual scanning for collision avoidance. The most effective method of scanning for other aircraft during daylight is to use a series of short, regularly spaced eye movements to search each 10-degree sector of the sky. Each area should be observed for at least 1 second. At night, pilots use peripheral vision by scanning small sectors and utilizing off-center viewing. This requires a slow scan. So you see that during the day we look right at objects, while at night you'll see traffic better by looking off slightly to the side of what you are viewing. Avoid bright lights at least 30 minutes before night flight, though your eyes usually adapt within 10. And once adapted, they return much quicker after viewing a bright object. VFR approaches to land at night should be made at the same airspeed and the same flight attitude as during the daytime. If you're ever on a collision course, there will be no apparent movement between your aircraft and the other aircraft. And the last thing to know about scanning is prior to starting each maneuver, you should visually scan the entire area for collision avoidance. This applies to in-flight maneuvers and the departure area of the runway. Well, that's it for the Airman's Information Manual. I sure hope you get a copy. It's only $6 or $7, and you'll get a lot of useful information here.
We'll start the AIM questions on page 12 with question 151. What type of oxygen should be used to replenish an aircraft's oxygen system for high-altitude flights?
The answer is number 4. Aviation breathing oxygen is the only thing you'd ever want to use.
Let's go to page 17, question 211. In radio communications, the phrase "have numbers" indicates that the pilot has
Number 2, wind, runway, and altimeter setting at that airport.
212. When flying easy, November 29er Sierra, the proper phraseology for initial contact with Buffalo approach control is Buffalo approach.
Number 4, easy 29er Sierra.
Question 213. When flying Hawk November 666 Charlie Bravo, the proper phraseology for initial contact with McAllister Flight Service Station is?
Well, as you remember, a flight service station is referred to as radio. Why? I don't know. I'm not sure anybody knows nowadays. But the answer is number 1, McAllister Radio, Hawk 666 Charlie Bravo.
Question 214. When flying breezy November 558 Niner, the proper phraseology for initial contact with Seattle EFIS, or En route Flight Advisory Service, is?
Well, we know that an En route Flight Advisory Service is Flight Watch. The frequency is 122.0. The answer is number 3, Seattle Flight Watch, breezy 558 Niner.
Question 215. The correct method of stating 4,500 feet MSL to air traffic control is?
Number 4, 4,500.
216. The correct method of stating 10,500 feet MSL to ATC is?
Number 3, 10,500. I would just like to mention that you're going to hear, as a student pilot, other students say in phrases and phraseology 100 different ways. And sometimes in the airlines you hear a lot of discrepancies too. There's really only one right way to do it, and this is all spelled out in the Airman's Information Manual, and hopefully your instructor knows the right way to do it and will impart that knowledge upon you.
It's almost a John Wayne effect where people think, they've got a couple thousand hours under the belt, now they're Rambo in the skies and they can, use whatever phraseology that they want to. And in fact, that's a rather dangerous situation because people will jump into or answer other people's calls. If you don't use the correct terminology, then the tendency is there to mistake a radio call, either from air traffic control standpoint or from your standpoint.
The most common mistake you'll hear people make on 216 is answer number 2, 10.5. Just don't put any of your personality in your communications. It's an exact science. As far as we're concerned, there's only one right way to do everything in here.
Next question will be 413 on page 34.
Oh, we're making progress, Jeff. I like those big jumps.
Prior to every flight, a pilot should at least...
Number 3, perform a walk-around inspection of the aircraft. We'll be talking about a similar question under regulations. It's interesting to note number 2, drain fuel from each quick drain. Well, you're going to want to do that, but that's not what they're looking for here. Check the required documents aboard the aircraft. That's rarely done before each flight. And number 1, check the operation of the ELT. That's not done either.
Question 414. What special check should be made on an aircraft during pre-flight after it has been stored an extended period of time?
Well, number 3, you want to check for damage or obstruction caused by animal, birds, or insects. And often birds or little animals can make a nest somewhere in the engine in the cowling where it isn't as noticeable as you might think, which could then restrict some of the cooling to that part of a cylinder and cause engine damage.
Question 415. The use of a written checklist for pre-flight inspection and starting the engines is recommended.
Number 4, to ensure that all necessary items are checked in a logical sequence.
Next page, question 424. Wingtip vortices, the dangerous turbulence that might be encountered behind a large aircraft, are created only when that aircraft is
developing lift. Answer number 3.
Question 425. Wingtip vortices created by large aircraft tend to...
The reason they're hazardous, or the reason we can get into trouble with them, is they tend to sink below the aircraft generating the turbulence and then stop or settle down after about 1,000 feet and stay there. Answer number 1 would be correct.
Question 426. When taking off or landing at a busy airport where heavy aircraft are operating, one should be particularly alert to the hazards of wingtip vortices because this turbulence tends to...
Number 3, sink into the flight path of aircraft operating below the aircraft generating the turbulence.
Question 427. The greatest vortex strength occurs when the generating aircraft is...
Well, heavy. The heavier he is, the worse it's going to be when he's clean. And clean means a clean configuration, gear and flaps up, and slow, which would be in takeoff or landing, which is when it's of a concern to us general aviation pilots.
Question 428. The wind condition that requires maximum caution when avoiding wing turbulence on landing is a...
It's a light quartering tailwind because that'll tend to blow the vortice right back onto the center line of the runway.
Question 429. When departing behind a heavy aircraft, the pilot should avoid wake turbulence by maneuvering the aircraft.
Number 2, above and upwind from the heavy aircraft.
Question 430. When landing behind a large aircraft, the pilot should avoid wake turbulence by staying...
Number 1, above the large aircraft's final approach path and landing beyond the large aircraft's touchdown point. That's exactly what you do when you're operating, which sometimes might be for the first time by yourself as a private pilot at a large airport. Just stay above him, land beyond the point he lands, and you won't have any trouble with wake turbulence.
Next page, question 431. What is the general direction of movement of the other aircraft during a night flight if you observe a steady red light and a flashing red light ahead and at the same altitude?
We've put questions dealing with this both here and in federal aviation regulations, and we're going to give this a pretty good working over under the federal aviation regulations, but the questions appear in both spots. The answer is number 1, the other aircraft is crossing to the left, and let's look at why. I always have to sit and kind of think these out slowly, and just because they don't come that easy. So we remember red is on the left with position lights, green is on the right, white is on the tail, and there's a rotating beacon. And they say that we see a steady red light and a flashing red light. Well, I'm thinking the only way I could see a flashing red light is if I'm looking at the left wing, and that would mean the aircraft is crossing to the left, or from right to left. So answer number 1 would be correct. But we'll cover more of this in federal aviation regulations.
And I like to think that the rotating beacon is what you're seeing, the red, the flashing red. So no matter what direction you were, you'd actually be seeing that flashing red light. The steady red light is the position light. So you're actually seeing a wingtip. And if the red light is on the left wing, Steady red, that means that you are looking at the left wing. So if you're looking at the left wing, it is going somewhere from right to left. Just position an imaginary airplane in front of you. Think, here's a left wing with the red steady light. The only way you can see that steady red light is if he's going right to left. It could be kind of coming towards you or away from you, but it's still right to left. Question 432. What is the general direction of movement of the other aircraft if during a night flight you observe a steady white light and a flashing red light ahead and at the same altitude?
Well, what the problem is saying is that we can't see the position lights on the wings, and the reason we can't is because we're behind the aircraft. They're not visible from 360 degrees. I think it's a 225-degree path or viewing area from the side or front of the airplane. So number 4 would be correct. The other aircraft is headed away from you.
You're actually looking at the tail of the airplane. The white light, remember, is the tail light, and this, of course, the flashing red light is the plane position, or the beacon, rotating beacon, and that
on the belly.
Belly or tail, depending on the airplane, yeah. Or in some airplanes, it's even on both. You have 2 beacons, both on the one on top and one on bottom of the fuselage. Question 433. What is the general direction of the movement of the other aircraft if during a night flight you observe steady red and green lights ahead and at the same altitude?
Well, this is the situation you want to be most cautious of, and very probably the other aircraft is approaching directly head-on. What you really, in real life, would want to watch out is for movement. If you see this and you see no movement, then you're on a collision course, and that is what's indicative of a collision course, is no movement, no visual movement of that other aircraft. So answer number 3 is correct. The other aircraft is approaching head-on.
Question 434. VFR approaches to land at night should be made.
Well, number 4, the same as during the daytime. The airplane doesn't know the difference between day and night. The airspeed isn't any different. And they tend to want to lead you into an answer here that you would take a higher airspeed at night. Well, as a student pilot, you might think that adds a little safety factor for you, and it might, but that's not a proper procedure. We fly airplanes the same at night as we do during the daytime.
Question 435. The best method to use when looking for other traffic at night is to?
Well, number 2, to look to the side of the object and to scan slowly.
Question 436. The segmented circle shown in figure 43, so why don't you turn back to the appendix section and find figure 43, indicates that the airport traffic is?
All right, let's take a look at figure 43, and we see these little L shapes around a circle. We have to ask ourselves, well, what are we looking at? A lot of this we have to imagine. First, let's take the situation of the wind. The wind would be, the cone fills up, the thick end points the direction the wind's coming from, and the thin end is the way the wind is moving. I'm sure you've all seen wind socks or a wind cone before. So the wind's out of the northwest. We know we always want to take off or land a plane into the wind, so 2 runways we could see that we wouldn't want to use in this situation would be this runway here landing to the east, or this runway here coming from the north landing to the south. So any answers in the problem that would deal with an easterly runway, let's say 090, or a southerly runway on a heading of 180, we could eliminate.
So they have runway, answer 2, right hand for runway 9, we can throw that one out.
Yeah,
and answer 1, runway 17, we can throw that out.
And let's take a look at number 3, right hand for runway 35. Okay, we've talked about the wind and which runway we're going to use. Now let's talk about which direction they want us to make our turns. We know that standard traffic is left turns and non-standard traffic is right turns. We can see here that if we were making an approach to the north, and we have north marked on the chart here, we would make left turns. If we were approaching to the south, we'd make right turns. So number 3 says right-hand traffic for runway 35. Well, this indicates that it's left-hand traffic, so we can immediately throw that answer out as being wrong without even reading the rest of it. We've eliminated the other 3 answers, so we know number 4 is correct, but let's look at why. It says left-hand for runway 35. Well, let's see if initially that's correct. You bet. We're making left-hand turns to runway 35 and a right-hand to runway 17. This would be right-hand traffic to 17. In this problem, they didn't take into consideration the wind. All they wanted to ask is if you can identify a north runway, or that the heading 35 is close to a heading of 360 or 360 degrees, and that you would make a left turn to go there. You also remember that whenever we're talking about runways, we drop the 0. So runway 35 is really a runway with a heading of 350 degrees, or technically anywhere between 345 and 355 degrees would label the runway 350, and of course it's magnetic. The reason it's magnetic is so when you line up on a runway, your compass should be in general agreement with that runway number.
Okay, let's go to question 437 now. The traffic patterns indicated in the segmented circle depicted in figure 43, that's the same figure that we just talked about, have been arranged to avoid flights over an area to the...
Okay, well, we know that standard traffic patterns are to the left, but they've indicated some are to the right here. If we're making an approach to the north runway, we're making left turns. If we make an approach to the west, we're making right turns. What they're doing is they're keeping traffic away from the southeast part of the airport here. Every other area we see making left turns to the east, or making right turns to the south, or making left turns to land to the north, all put aircraft in this area. But what we've seen is there is no movement here. So let's see if there's an answer that jives. Number 3, that southeast of the airport is the area that they have that is arranged to avoid flights over that area.
Question 438. The segmented circle depicted in figure 43 again indicates that a landing on runway 26 will be with a...
Okay, well, the first thing we have to ask ourselves is with runway 26, a heading at 260 degrees is almost west, or 270, so they're talking about making an approach from the east and landing to the west. We can see here that we would be making a turn in which direction? A right-hand turn. It'd be non-standard. And let's ask ourselves what the wind would be doing. If we didn't do anything to correct for wind, it's going to want to blow us this direction as we're lined up on final. So we would take a crab to the right. Let's see if we have an answer that says right turns and a crab to the right. Well, it says we have a right quartering headwind, which would be the same thing.
Okay, question 439. Which runway and traffic pattern should be used as indicated by the wind cone in the segmented circle depicted in figure 43? And I think we all recognize what 43 is telling us by now.
Yeah, and we really talked about the answer to this one when we took the first question in 436. The answer is number 3. We want left-hand traffic to runway 35. If you read the other answers, they're all wrong.
Question 440. An airport's rotating beacon operated during the daylight hours indicates...
Well, this is a question we'll run into regulations or cover more in regulations, but it's also Airman's Information Manual type of information that you'll find in that publication. The answer is number 2, that the weather in the control zone is below basic VFR weather minimums, but we'll be coming to that and talking to that more in another module.
Question 441. Airport taxiway edge lights are identified at night by...
Well, one way to remember this is next time you're in an airliner, just take a look at what's off to your left and you'll see lots of blue lights. So it's blue omnidirectional lights, answer number 2.
And the white lights, one of the answers is white, that's the runway. Alternating red and green, that's a threshold or something. I don't know what
I don't even know if it exists.
Yeah.
I've never heard of it.
Amber would be runway also, I guess. Some runway center line would be white and the amber along the side.
We're talking with an airline pilot with 9,000 hours, and he isn't even sure what 2 of the alternate answers are, so you can take our word for it that answer number 2, or blue lights, are correct.
Question 443. To set the high-intensity runway lights on medium intensity, the pilot should click the microphone 7 times, then click it.
Well, you'll find this by reading in the Airman's Information Manual, answer number 3, 5 times.
It's called pilot-controlled lighting, by the way, when you set the lighting intensity with the microphone on the frequency listed, the CTAF frequency or Unicom frequency, whatever frequency is listed. Question 444. How can a military airport be identified at night?
Well, civilian airports have 1 green and 1 white flash with 1 complete circuit of the beacon. The way you can differentiate that between a military airport is the military airport has 2 quick white flashes and a green, and answer number 2. 2 dual peaked or 2 quick white flashes between green flashes.
Question.
I just want to comment. You never want to land in a military field. They'll confiscate your airplane. You'll probably lose your license, and it happens in Denver a lot. We have a military field, a air guard field called Buckley that has the same runway alignments or close to the same alignments as Centennial, and there have been quite a few pilots accidentally approach and land there, and they land, and sometimes they have to disassemble the plane to get it out.
You shouldn't land on a military runway unless you have authority or approval to do so. Some military airports are dual use, but the dual use airports, by dual use I mean both the military and the civilian traffic use that particular airport. Usually a dual use airport just has 1 white light and then 1 green, but a dual white flash beacon is strictly military, and so stay away from them unless, like we said, you have authority to land. Let's move to next page, question 445. When approaching to land on a runway served by a VASI, or visual approach slope indicator, the pilot shall...
Well, number 3, maintain an altitude at or above the glide slope. And that's, of course, until you're in a position to land the airplane.
Question 446. An on-glide slope indication from a tricolor VASI is...
You'll know, and we've talked or will be talking about the fact that generally in aviation, anything that's green is okay and anything that's red is not. Just understanding that one bit of information will help you answer these questions about different lighting schemes to help you follow the right approach angle to the runway or to your landing point. It's answer number 2, a green light.
So you're on glide slope on a tricolor VASI with a green light. 447. An above glide slope indication from a tricolor VASI is?
Well, it's an amber light, number 3.
448. A below glide slope indication from a tricolor VASI is?
We've eliminated about everything. It would be red, answer number 4.
Question 449. A slightly high glide slope indication from a precision approach path indicator, that's also abbreviated PAPI, P-A-P-I, is?
Well, number 2, 3 white lights and 1 red light, just like we saw in the curriculum.
Question 450. A below glide slope indication from a pulsating approach slope indicator is?
It was funny because I have never seen one of these in all my flying days, and so I asked Jeff if he ever had seen one, and he said, yeah, you saw one in San Diego?
San Diego, right.
Anywhere else you've ever seen one?
One military field in the Philippines years ago. Yeah.
Okay, which means it's not very common if he's only seen it once and I've never seen it. The answer is number 4, a pulsating red light, and you're just going to have to memorize that verbatim.
I should mention the only reason why it was pulsating was to let pilots know that it had a steeper than normal glide path angle. And the last time I went into San Diego, Steve, the VASI was not pulsating. So I don't know if they've changed the VASI angle or they've just removed it from that particular field.
An interesting item, too, is this is the first time we've ever seen this on the FAA exams. And I don't expect that they're going to put a lot of these into use.
Question 451. Illustration A in figure 44 indicates that an aircraft is...
Well, let's just review VASI. White over white, you're too high. Red over white is all right. And red over red, you're dead. That should be pretty easy to remember. White over white, you're too high. We've always made the reference that most illegal drugs are white. So white, white, you're high.
White over white, out of sight is how I remember it.
Yeah, and red over white is all right. That rhymes. And red over red, you're dead. So looking at number A, red over white, we're all right, means we have an on-glide slope indication, and answer number 3 would be correct.
Question 452, also referring to figure 44. While on final approach to a runway equipped with a standard 2-bar VASI, the lights appear as shown by illustration D in figure 44. This means that the pilot is...
I just can't wait to get the words out of my mouth. Red over red, you're dead. But you're not dead till you hit the ground and kill yourself, so you're just below glide slope. And answer number 3 would be correct.
Question 453. VASI lights appearing as shown by illustration C in figure 44 would indicate that an airplane is...
Well, white over white, you're too high. We're too high. Let's see if we have an answer like that above the glide slope, number 4.
You know, it's interesting, Steve, that figure has on glide slope, below glide slope, and above glide slope, and figure B, or area B, is showing white over red, and I have never seen white over red.
That is if you would be inverted, going...
on glide slope,
on
upside
glide
down.
slope, upside down, and hopefully you have main landing gear on the cabin top or the roof of your airplane. So B is just something to throw you. It doesn't exist, and you'll never see it unless you're inverted.
Yeah, and hopefully we won't ever be.
Yeah, it'd be a little close to the ground. Remember, well, we'll talk about it in regulations, but you have to be 1,500 feet above ground level to do aerobatics. You have to have a parachute on, too.
Okay, let's move to the next question, which is question 452, and this refers to figure, I'm sorry, not 454, and it refers to figure 45. 454, that portion of the runway identified by the letter A in figure 45.
Well, that's easy. It's a displaced threshold. You're going to see these all the time in real life if you haven't seen them already. And what this area means between A and B is it's okay for taxi or takeoff, but it's not okay for landing. And answer number 2 fits our term. May be used for taxi or takeoffs, but not for landings.
Question 455. Which statement is true according to the airport diagram shown in figure 45?
Well, I'll tell you that answer number 4 is correct, and let's look at why. Takeoffs may be started at position A on runway 12, and the landing portion of this runway begins at B It's just what we just explained. It's called a displaced threshold.
Question 456. What is the difference between area A and area E on the airport depicted in figure 45?
Okay, well, A is a displaced threshold, and it's okay to use it for taxi and takeoff, but not for landing. If we move down to area E here, and it's a very small illustration, we see that this is an overrun. Overrun can't be used for anything. It's just that, an overrun. So let's see if we have an answer that fits. Answer 1, A may be used for taxi and takeoff. E may be used only as an overrun.
And an overrun is really to be used only during an emergency. So if you had let's say we landed and we lost our brakes for some reason, obviously you wouldn't be violated if you ran into the overrun just trying to stop the airplane. But that's the only time you would use an overrun, is if you were in an emergency.
If you overrun the runway.
Yeah, exactly.
Okay.
Funny how they name things sometimes so they're accurate.
That is funny, isn't it? 457.
457. Area C on the airport depicted in figure 45 is classified as...
Well, I'd expect you to be able to get this one right without any aviation knowledge. With X's all the way across the runway, it means only one thing: the runway is closed. Can't use it. And be careful using something like this for an emergency out in the middle of nowhere. Drag strips are often look like runways from the air.
Or they may be former runways, yeah.
Yeah, or former runways, but often to prevent people from drag racing except on the weekends or the prescribed times, they put a chain across there, and it could be marked with X's as a closed runway. So you would never want to make an approach there unless you had to. If I ever had to land on a closed runway, I would definitely want to do it with power so I could drag the field first, make sure there were no obstructions, then make my approach and landing, and only in a real emergency situation.
We'll turn to the next page then. Question 458. Select the proper traffic pattern and runway for a landing as indicated on the airport diagram in figure 46. Different figure now down at the bottom of the page.
Okay, figure 46 addresses the same problem as figure 43 did with the wind cone, except they have just a little different way of presenting the information, and they're showing us the runways. And this is more what you might see in real life out at an airport. We can see that the wind is out of the southwest. It's blowing from the southwest to the northeast.
This is not a wind cone, right? This is a wind tetrahedron or whatever. So the pointed, it's just like an airplane will point into the wind. That pointed shape will point into the wind.
Right, and the butt will be, or the butt of it, or the end of it will face the wind the directions come. So the wind's coming out of the southwest, and immediately we could see that runway 22, or heading at 220 degrees, would work because that's into the wind, or heading to the south would be acceptable. We'd have a right crosswind going to the south. Just looking at this chart, we could see that landing to the north would be with a left quartering tailwind, something we don't want, and landing on runway 4 would be directly downwind, something we don't do either if we don't have to. We can see right here that runway 22 and runway 4 is a closed runway, so we're not even going to pick that for an answer. We can also see that there's a displaced threshold at runway 36 and runway 18. That pretty much takes the chart apart except for the traffic indicators. Let's look at the problems and see what we've got.
It's 458 there, top of the page.
We would make right-hand traffic and use runway 18, which is answer number 2. We see if we're making a landing to the south, the indication here is right traffic or right turns.
Correct. Okay, let's go to question 459 now. If the wind is as shown by the landing direction indicator in figure 46, the pilot should land to the...
Okay, if the wind is shown as by the landing indicator in figure 46,
That's right.
okay, the winds are coming out of the south, which means we'd want to make a landing to the south. So we'd want to land on runway 18, and we'd have a crosswind from, we looked at this before, from the right. Let's see if we have an answer that looks like that. Answer 2, south on runway 18 and expect a crosswind from the right. Let's just look at the alternate answers anyways. North on runway 36 and expect a crosswind from the right. Well, if we landed north on runway 36, would we have a crosswind from the right?
Well, they're also asking, Steve, which way should you land? And you wouldn't want to land to the north with the wind from the southwest.
Plus, you'd be landing with a tailwind.
Yeah.
Let's look at answer number 3. Land southwest on runway 22. We know that wouldn't be correct because it's a closed runway. Or land northeast on runway 4. That would be directly downwind on a closed runway 2. So we can see the only correct answer is number 2.
Okay, question 460. The arrows that appear at the end of the north-south runway as shown in figure 46 indicate that the area...
Well, we're talking about the displaced threshold here at runway 36 and runway 18, and we're wearing this one out. We know that it can be used for taxi and takeoff and not for landing. Let's see if we have an answer that looks like that. Number 3, cannot be used for landing, but may be used for taxi and takeoff.
Well, we're through with that chart now. Let's go to question 461. The numbers 9 and 27 on a runway indicate the runway is oriented approximately.
Sometimes I worry that I use a few many words in explaining my answers to the questions, and I like to work with alternate answers a little bit too, but it's not within the scope of the course to do it. So we've covered this just by talking about runway alignment, that 9 is 090 or 90 degrees, and 27 we add a 0, it would be 270 degrees. And the answer number 1, 090 and 270, magnetic. 3 would be wrong because it says true.
Question 466 on the same page. Basic radar service in the terminal radar program is best described as?
Number 1, traffic advisories and limited vectoring to VFR aircraft.
467. Stage 3 service in the terminal radar program provides?
Number 3, sequencing and separation for participating VFR aircraft.
468. From whom should a departing VFR aircraft request Stage 2 Terminal Radar Advisory Service, it's also called a TERSA, during ground operations?
Well, the only one you can talk to during ground operations at an airport is ground control, and that's who we'd make our request to. At a larger airport, you'll find clearance delivery, but that's not asked on the private pilot exam.
Question 469. If radar traffic information is desired, which action should a pilot take prior to entering a TERSA?
Well, when we talk about prior to entering, we're talking about approach, or we're getting ready to enter an area of an airport. So number 1 would be correct. Prior to entering the TRSA, contact approach control on the appropriate frequency, and you'd find that frequency on your VFR charts.
Next page, question 475. ATIS is the continuous broadcast of recorded information.
Number 3, concerning non-control information in selected high-activity terminal areas.
476. How should a VFR flight plan be closed at the completion of the flight at a controlled airport?
Well, number 2, the pilot must close the flight plan with the nearest FSS or other FAA facility upon landing.
477. After landing at a tower-controlled airport, when should the pilot contact ground control?
You only contact ground control when the tower tells you to do so. And there might be a real good reason, conflicting traffic, or the other party up there, the other controller is off on a coffee break. Sometimes the tower will take you all the way to your tie-down area, and that's completely okay and completely legal for the controller to do that.
So it's answer 4.
Yes.
Question 478. If instructed by ground control to taxi to runway 9, the pilot may proceed.
Well, clearance to taxi to a runway is clearance to cross all taxiways and intersecting runways up to but not on the runway you've been cleared to. So number 1, via taxiways and across runways to but not onto runway 9.
Question 479. An air traffic control radar facility issues the following advisory to a pilot flying on a heading of 090. Traffic, 3 o'clock, 2 miles, westbound. Where should the pilot look for this traffic?
Okay, well, if our heading is 090, we're heading east. And if I'm heading east right now and he tells me I have traffic at 3 o'clock, I just think of a clock in front of me and look at number 3 and see that's off to my right. Well, if I'm heading east and I've got something 90 degrees or off to my right, that would be directly south. Let's see if we have an answer. Answer 2, south.
Question 480. An air traffic control radar facility issues the following advisory to a pilot flying on a heading of 360 degrees. Traffic, 10 o'clock, 2 miles, southbound.
Well, initially we'll just look at the beginning of the problem. It says we're on a heading of 360 degrees. Well, we know that is north. They've told us, if we're heading north, they've told us that our traffic is off at our 10 o'clock position, which would be to the left, which would be northwest of us. See if we have an answer that fits it. We do, number 1.
Next page, question 481. An air traffic control radar facility issues the following advisory to a pilot during a local flight. Traffic, 2 o'clock, 5 miles, northbound. Where should the pilot look for this traffic?
Well, answer number 4 is correct, between directly ahead and 90 degrees to the right.
Question 482. An air traffic control radar facility issues the following advisory to a pilot flying north in a calm wind. Traffic, 9 o'clock, 2 miles, southbound. Where should the pilot look for this traffic?
Well, he'd look to the west, or answer number 3.
Skip down to 484. If the aircraft's radio fails, What is the recommended procedure when landing at a controlled airport?
Well, this might sound like you're in violation of the regulations because at a controlled airport, that's referring to an airport traffic area. And we're going to get into all that, but that's an area 5 statute miles from the geographical center of the airport up to, but not including 3,000 feet. And when there's an operating control tower at an airport, you need to be in radio communication with that control tower before entering. Except if you have a broken radio, you're allowed to observe the traffic flow, enter the pattern, and look for a light signal from the tower. Answer number 1.
Skip to 488. When approaching Lincoln Municipal, figure 47, from the west at noon, for the purpose of landing, the initial communications should be with...
Okay, if we take a look at the airport facility directory on in Appendix 3, figure 47, which is on page 33 in your appendix, we, of course, would contact approach control, and we can see up here in this fine print, it says approach and departure control 124.0. That would be our answer. And it says we're approaching from the west. They have different frequencies from different directions. We'd use 124.0 on a heading of 170 degrees to 349 degrees.
From the field, right.
From the field.
Right.
We'd use 124.8 from 350 to 169, or approaching from the east. So answer number 1 is correct. Lincoln approach on 124.0.
Question 489, also referring to figure 47. Which type radar service is listed for Lincoln Municipal?
Okay, once again, you need to read the fine point. It says stage 3, and it says to contact approach control to get that service. So we have stage 3 radar service. Let's see if there's an answer that looks like that. It says number 3, radar sequencing and separation for participating VFR aircraft, which is our definition for a TRSA or stage 3 service.
Question 490, also referring to figure 47. Traffic patterns in effect at Cook Municipal, figure 47 are, and that's down at the bottom of that figure.
Okay, what you just have to do is look at the alternate answers and look at the airport facility directory from McCook, and it says runway 03, it's got a VASI, and it says right traffic right at the end, RGT TFC. It means right-hand traffic for runway 3. See if we have an answer that looks like that. Okay, we've got that as part of an answer. I've got number 2 as the right answer, and let's take a look at why. It says we have left-hand traffic on runway 12 and 21. We do have a runway 12 and a runway 21. There's nothing here to indicate that there's non-standard traffic, so we assume, or what is correct, is left-hand traffic. So the first part of answer 2 is correct. It says and runway 30. Okay, we have runway 30 here. There still is no comment as to non-standard traffic, so far we're correct. And right-hand traffic to runway 03, we just looked at that different situation here, which would fill in what we needed for number 2. And funny enough, it's one of the longest answers. It's also the most correct answer, and answer 2 will be right for number 490.
Question 491, also referring to figure 47. Where is Loop City Municipal located with relation to the city?
Okay, well, we'll take a look at Loop City, and right here it says it's 1 mile northwest. Now, you might say, oh, okay, Steve, those were really easy for you to point out because you sat home last night and figured them all out and marked them up with a yellow pen, and that's correct. But in the first appendix behind the questions is a legend that shows you how to read this. Literally, you could get all these questions right, not knowing anything about aviation, never having opened a book, just by looking at the available information in the appendix and answering the question. They don't expect you to know how to read this thing as a student pilot, but with every airport facility directory in the same book as a legend, so you can look this information up, and that's how you'd go about answering these type of questions. As far as I'm concerned, this is free money on the exam. It takes no thought at all. It just takes you looking up the right information about how to read the chart, then reading the chart.
In order to do so, you need to know that the information is in the back of the book there in the Legends section. Question 492. What is the recommended communications procedure for landing at Lincoln Municipal during the hours when the tower is not in operation? And again, that's figure 47.
Okay, well, back to figure 47, and up here under the communications area at Lincoln Muni, it says CTAF, or Common Traffic Advisory Frequency, is 118.5. And that would be, of course, the tower frequency that we would use when the tower is in operation. We also see that Lincoln has a flight service station, which makes it an airport advisory area when the tower is closed, or within 10 statute miles around the center of the airport is an area controlled. Well, it's not controlled by flight service. They just give you traffic advisories and runway information. But those are the ones you would talk to. and you would talk to them on the tower frequency, not on the flight service station frequency. So answer number 4 is correct. Contact the Lincoln Flight Service Station on 118.5 for traffic advisories.
493. The most effective method of scanning for other aircraft for collision avoidance during daylight hours is to use...
Well, number 2, a series of short, regularly spaced eye movements to search each 10-degree sector.
And remember, the traffic that's dangerous is the traffic that's not moving against your windshield. So if you see an airplane out there that's moving relative to you, then more than likely you're not going to hit him unless he changes his heading or you change your heading. But the one that just is like a bug spot right out there in the windscreen, that's the one that's dangerous, and that's the one you're going to hit. Question 494. The most effective method of scanning for other aircraft for collision avoidance during nighttime hours is to use...
Number 3, peripheral vision by scanning small sectors and utilizing off-center viewing.
Question 495. What is the most effective way to use the eyes during night flight?
Well, number 2, to scan slowly to permit off-center viewing.
496. How can you determine if another aircraft is on a collision course with your aircraft?
Well, we've talked about this 2 or 3 times because we feel it's pretty important. And answer number 4, there will be no apparent relative motion between your aircraft and the other aircraft.
Question 497. Prior to starting each maneuver, a pilot should...
Number 4, visually scan the entire area for collision avoidance.
And I imagine your flight instructor is going to drum that into you and hit you over the head every time you do it without clearing the area.
Yeah, and what you do is your 290-degree clearing turns is what's most common, and that allows you to get a full view of the area you'll be working in.
Question 498. What procedure is recommended when climbing or descending VFR on an airway?
Number 4, execute gentle banks left and right for continuous visual scanning of the airspace.
Not enough, I might add, so that you appreciably change the position of the airplane. We're just changing the position of the airplane horizontally, I'm talking about. We're just changing the attitude of the airplane so that you can have full scanning of the airspace.
I'm not a very tall person, and I fly airplanes with high glare shields, and when I'm climbing, I can't see anywhere out in front of me. And as a standard practice, whenever I'm in that situation where I can't see, I always make gentle turns, 10 to 15-degree banks, about 20 or 30 degrees of heading change. And as an instructor, I use it with my students on every climb up from an airport, whether it's on an airway or not. It's never on an airway when we're leaving an airport, because it's a good coordination exercise and also allows you to see directly in front and below you.
Next, we're going to refer to the flight plan form. That's figure 48. If more than one cruising altitude is intended, which should be entered in block 7 of the flight plan?
Well, they only want one altitude there, and if you're going to use more than one, let's just give them the initial cruising altitude, or answer number 1.
Question 500, also referring to the flight plan form. The information that should be entered in block 9 on a VFR day flight is a...
Well, this answer's a little tough. Number 2 is correct. The name of the destination airport if no stopover for more than 1 hour is anticipated. That came right out of the Airman's Information Manual.
Question 501. What information should be entered in block 12 for a VFR day flight?
Well, as you know, what they want in block 12 is, it says fuel on board. They want your total fuel on board or your range. And the reason is if you get lost, they're going to need to establish an area that they're going to look for you, and they want to know how far you were capable of going based on your own abilities or your own engine. And so we want to put our total fuel on board here, the total usable fuel, in hours and minutes. And let's see if we have an answer like that. Number 4, the amount of usable fuel on board expressed in time.
Well, that completes the flight plan form. Now we'll go to question 502. If air traffic control advises that radar service is being terminated when the pilot is departing a terminal radar service area, or TERSA, the transponder should be set to code.
Well, don't let the TRSA throw you, because that has nothing to do with the question. Whenever you're on your own VFR, you'll squawk 1200.
Question 503. When making routine transponder code changes, pilots should avoid inadvertent selection of which codes?
Well, I'm sure you remember the 75, 76, and 7700. Answer number 2.
And by inadvertent, by the way, they mean while you're, let's say we're squawking 1200 and now we get into range of a Tersa and they tell us to squawk something else, you don't want to, while you're switching from 1200 to whatever they just told you to put on your transponder, to pass through 77 anything, not just 7700, but 7755 or 7726 or whatever, 7600 or 7500. Next page, question 504. In VFR conditions below 18,000 feet MSL, what transponder code should be selected?
Well, we covered that. It's code 1200, and the ident feature should not be engaged. It shouldn't be engaged unless you're told to squawk ident.
Question 505. The letters VHF, DF appearing in the airport facility directory for a certain airport indicate that.
Well, number 2, the flight service station has equipment with which to determine your direction from the station. A DF is a DF steer or direction finding steer, and all flight service station or air traffic control needs to get a fix on you is a transmission by you keying the microphone, which is all they'll ask you to do if they need to find you. This used to be very common years ago for finding lost aircraft. Nowadays it's hardly used because of the amount of radar coverage throughout the United States.
Question 506. To use VHF DF facilities for assistance in locating an aircraft's position, the aircraft must have.
Well, I just gave you the answer for that. Number 1, a VHF transmitter and receiver.
507. Who should the pilot contact to receive a special VFR departure clearance in a control zone co-located with an airport traffic area?
Well, like I mentioned, this will be really worked over in regulations, and it's answer number 2, the airport control tower.
Next we'll skip to page 48, question 576. Get into some physiology questions, or questions about
subject.
aviation physiology. 576, to preclude the effects of hypoxia.
Number 1, avoid flying above 10,000 feet MSL for prolonged periods without breathing supplemental oxygen, according to the FAA. That isn't what anybody does.
Remember, hypoxia is oxygen deprivation or oxygen starvation. They're just saying above 10,000 feet you might be starved for sufficient amount of oxygen. 577. Rapid or extra deep breathing while using oxygen can cause a condition known as.
Number 4, hyperventilation.
Question 578. A pilot should be able to overcome the symptoms or avoid future occurrences of hyperventilation by.
Well, it might sound a little stupid, but by slowing the breathing rate, which is what we're going to try to do, breathing into a bag or talking aloud. And I think breathing into a bag is kind of funny, Jeff. It's been in the Airman's Information Manual forever, and I don't know anyone that's breathed into a bag to prevent hyperventilation.
Question 579. Which would most likely result in hyperventilation?
Well, number 1, emotional tension, anxiety, or fear.
580. Large accumulations of carbon monoxide in the human body result in.
Well, it results in giving you the symptoms of hypoxia, and one of those symptoms is a sense of well-being. Answer 3 would be correct, an increased sense of well-being.
581. Susceptibility to carbon monoxide poisoning increases as.
Well, as altitude increases. Answer number 1.
582. A pilot is more subject to spatial disorientation if.
Well, number 4, body signals are used to interpret flight attitude. That's exactly what we don't want to do. Jeff explained under aircraft instruments that what you want to do is rely on your aircraft instruments regardless of any other situations around you. It's really the only thing you have to rely on in flight.
Question 583. A pilot experiences spatial disorientation during flight in a restricted visibility condition. The best way to overcome the effect is to.
Well, we just answered that one ahead of ourselves too. Number 4, rely upon the aircraft instrument indications.
584. A state of temporary confusion resulting from misleading information being sent to the brain by various sensory organs is defined as.
An FAA exam, or number 1, spatial disorientation.
Question 585. What preparation should a pilot make to adapt the eyes for night flying?
Well, I've heard 100 different things here, and only 4 is correct according to the FAA. Avoid bright white lights at least 30 minutes before the flight. In real life, if you avoid bright lights for 5 to 7 or 10 minutes, that'll really do the job. You don't need to really do this in real life. Do you pay any attention to this as an airline pilot at night?
I don't know about the 30-minute figure. We certainly do stay away from the bright lights and kind of facetiously talk about rigging for night running, but we'll turn all the lights down several minutes, say 20, 25 minutes before we get into the area where we're going to be using instruments, in a nighttime situation.
Okay.
586. The danger of spatial disorientation during flight in poor visual conditions may be reduced by.
Well, number 2, having faith in the instruments rather than taking a chance on the sensory organs.
587. Which technique should a pilot use to scan for traffic to the right and left during straight and level flight?
Number 1, systematically focus on different segments of the sky for short intervals.
And the last question under the AIM, 588. What effect does haze have on the ability to see traffic or terrain features during flight?
Well, we had a little trouble finding an answer for this, and I called Jeff, and Jeff looked it up, and he called me, and I looked it up, and we decided 4 was the most correct. All traffic or terrain features appear to be farther away than their actual distance. We felt number 1 was a pretty good answer, too, in real life, but 4 is what we're going to go for the test.
Thanks, Steve. Well, that covers our AIM questions section, and we have covered every one of the questions that the FAA asks in this section, some 89 questions. It's just a small sampling of the entire information found in the AIM, or Airman's Information Manual, and you really should get a copy of that and read through it at your free time, because there's a wealth of tremendous information, very informative, and information that you're going to be required to know during your flying career.